Today we're going to be beginning solutions, and I want to start by talking about the objectives. Now, today also has a pretty lengthy reading assignment with it, and after the reading you should be able to do all of these things. And the important thing here that I would draw your attention to is that this last one, propose a procedure to differentiate between a solution, suspension, and colloid. This is an application problem, right? And everybody knows how much Mr. Ryan loves application problems. So keep that in mind as you go through this section and see if you can figure some stuff out. And then today we're going to focus on these things. And so this is all very like basic, you can read it and pick it up information. And then today we're going to build a little bit more. I am going to review some of this stuff. So if you're feeling confident, you can skip sections that you feel confident about. Okay, now to begin, I would like you to fill out this table as best you can. And what I want in here is I want basically descriptors of everything. Describe everything that you can think of for each of these types of mixtures. All right? So pause it, write some stuff, and then compare to what I get. All right, so the first thing that I'm going to do is I'm going to talk about whether or not these are homogeneous or heterogeneous. And solutions are the only homogeneous ones. Okay, so which means a colloid and a suspension are both heterogeneous. Okay, the next thing that I think differentiates these, this is one thing, the next thing that I think is the size of the particle. And solutions, and by particle I mean the solute rather than the solvent. Okay, so solutions have very small particles. Okay. Colloids have medium-sized particles. And suspensions have very large particles. All right, solutions do not settle out. The same can be said for colloids. These also do not settle out. Okay, but a suspension will. The particles will settle out because they're so large. Because the particles are so large in a suspension, you can also filter them. Whereas these other ones, the particles are so small that they'll just go right through a filter. Okay. Now, colloids have something called the Tyndall effect. Okay, which is that the particles scatter light. Okay. Solutions do not scatter light. Okay, and suspensions are weird. They normally don't, but if the particles are on the small end of this scale, okay, like if they're closer to the size of a colloid rather than a suspension, then they could. Yeah. So you just gotta be a little aware of what's going on with those. Okay, so let's look at some examples of each type. How about examples of a solute solvent system? So how about something like sugar as the solute? Okay, and the solute is the thing that's being dissolved. and the solvent is the thing that's doing the dissolving. Okay, now sometimes the solute, so sugar, and let's say that this is in water. Okay, now I could also do something where I say water is dissolved in ethanol. Okay, now how would I know, in this case, which is the solvent and which is the solute? Well, in these cases, the solvent will have a larger volume. Okay, so whichever one's just more, that's going to do the dissolving. Okay, another example that I think is pretty clever is gold. Is gold a good example of a solution? Yeah, you betcha. Okay, so 24 karat gold is pure gold, okay? And the way that the carat scale is set up is the carat is set up as 24 times the mass of pure gold over the total mass. All right, so if your mass of pure gold equals the total mass, as in it's pure gold, you get you multiply that by 24 and you get 24 karat gold. Okay, if you're about half gold, okay, you'd be about 12 carats. So a 14 karat gold is an alloy with gold and silver and copper. Okay, and 14 karat gold is 14/24 or 58.3% gold. Okay, and it has all these other atoms in it. Now, why would you do that? Well, pure gold is actually very soft. It does not make very good jewelry because it scratches very easily, it dings very easily. You have to get it refinished all the time. Whereas something like 12 or 14 karat gold, they are much more sturdy, much more stable jewelry. Okay? So, what about suspensions? So suspensions, there's an example that I really like. It's pulpy orange juice. And I have here an example, okay, of a suspension. Okay. So there's a bunch of water molecules that are very small, and then there's the orange pulp. Okay. So the orange pulp is much, much larger than the water molecules. And if you leave your pulpy orange juice sitting out on the table, then eventually the pulp settles to the bottom, right? And you got to shake it back up. Otherwise, you're going to have no pulp at the top, and then your last couple drinks will be just all pulp, and it'll be more chewy than drinky. Okay, so the last one is colloids. Okay, now one of the things that I thought was an interesting colloid is water droplets suspended in air. Okay, so water droplets, okay, would be your solute. Okay, we don't really use these terms for colloids, but and then your solvent would be the air. Okay, and you've all seen this. Okay, if it's very foggy out, you'll see cars driving down, and you can see the headlights. Okay, and you normally can't see the headlights because the light rays travel in a straight line unless they hit something. Okay, and unless they're scattered. So what's happening is, okay, here's light coming out of the headlight. It hits a particle and gets deflected by the light, so you can see it. Okay, so this is the Tyndall effect. This is an example of Tyndall effect. Okay, I have a short video on solutions that I think is quite good.
A solution may appear to be a single substance, but it is actually the result of the mixture of a solvent and one or more solutes. Here, the girl is dissolving salt into water to make the solution for a saltwater aquarium. In this example, Salt is the solute and water is the solvent.
Salt water is a homogeneous mixture containing sodium and chloride ions and water molecules uniformly distributed throughout the solution.
This table shows examples of other combinations of solutes and solvents. In each case, the substance with greater volume is designated the solvent.
Okay, so here you'll see some more examples of solutions, all right? A gas and a gas, so oxygen and nitrogen. Remember that air is mostly nitrogen, okay? A gas and a liquid, think of like carbon dioxide and water, like a soft drink. Solid and a liquid, sea salt, salt water, sugar water. This is the one that a lot of people think of, okay? And a solid and a solid, so that's like gold. 14 karat gold is a solid mixed in a solid. Okay. All right, so that's sort of the end of the review section, and now we're going to talk about sort of the more application-y, more challenging materials today, which will be this stuff. Okay, so my first question is, what factors affect the rate at which a solid solute dissolves in a liquid solvent? Well, before I answer that, I want to talk about what actually like the solution process is. What actually happens when a solid dissolves in a liquid. Okay, and for this, I'm going to take an ionic compound, and ionic compounds make pretty good model systems for this. All right, so here I have, this is lithium chloride. Okay, and I'm going to begin with a crystal lattice, you should remember, of solid lithium chloride. I'm going to drop that in water. Okay, now water begins to interact with the ions on the surface of the lattice. Now keep in mind that water, okay, remember water has this dipole. So there's a partial positive charge down here and a partial negative charge up here. Well, the partial negative charge would be attracted to the positive ions, okay, the lithium ions, and the partial positive would be attracted to these chloride ions, okay? So water begins to interact with the ions on the surface of the lattice because of this charge. Water molecules are able to completely surround an ion and break it away from the lattice. Okay, and when you do, that ion goes, quote, into solution. All right, because it's completely surrounded by waters. Now this happens because the interactions between water and the ions are stronger than the interactions within a lattice. Now, most of the time, this is because there are more interactions. So, where in a lattice, a lithium ion might interact with 2, 4, let's say 4, okay? 4 chloride ions. In solution, it's going to be surrounded by a whole bunch of waters, okay? You can think these 4, there might be more there. There's a top, there's a bottom, there's basically, it's going to be completely surrounded. So there are going to be more interactions, all right? This process is called hydration when done in water. Okay, if you have a different solvent, let's say your solvent is ethanol, it's going to be similar, okay, but we won't call the process hydration. So how could I get this to speed up? Well, to answer this, I think I'm going to go to a video.
The more opportunities a molecule of solvent has to come in contact with a solute, the faster the solute will dissolve. If the solute is broken down into small chunks, it has a greater surface area and dissolves more readily. In both cases, however, the dissolved first layer has to drift away before the next layer can dissolve. Stirring, shaking, or otherwise agitating the solution further speeds up the dissolving process, sweeping away the dissolved layer and exposing more solute to the solvent. Increasing the temperature increases the speed of the molecules. The faster they move, the faster the solute dissolves. For example, sugar added to hot tea dissolves almost immediately, while sugar in iced tea normally needs a lot of stirring.
Okay, so that should make sense, right? So the first one was you break up the solid, okay? You break it down, and that increases surface area. Now, I remember there's a joke that goes around with biology. You get to a certain point of the year and all the answers have to do with increased surface area. Well, it's very important, right? So if you increase the surface area of your solid, and I'm going to go back to my diagram here, okay? If you increase the surface area of the solid, more waters can interact with it. So, you know, if you have a big square, okay, let's say you have a big square, and let's say that we live on flat world or whatever that thing's called, okay? You have this much surface area. But if I take that and I break it down into a bunch of tiny little squares, okay, I'm going to greatly increase the surface area, all right? And by greatly increasing the surface area, I'm going to allow more water to get at the surface of the crystal lattice, and thus the solution process should happen faster. All right. Now the second one was stirring. Okay. If you have a big pile of solid on, okay, let's say here's a glass. Okay, and I have a big pile of solid here. Okay, only this top layer up here of solid is interacting with the liquid. Okay, this stuff down here, there's no water getting in there. Okay, but if you stir this up, then you're getting water all over the place. Okay, so it's sort of another way of increasing surface area. Actually, it's kind of cheating. They're really kind of the same, right? So the last one is to give those water molecules more energy, because the water molecules have to get in there and kind of break the interactions, the intermolecular forces between ions in the crystal lattice. So if they have more energy, they're better able to do that, all right? So all of that should make sense on a molecular level. Okay, now one of the things, I want to go back. There's another good video here. By the way, these are all from our textbook. There's another good video here
There
about
are limits on the amount of solid solute that will dissolve in a solvent. The amount depends on the nature of the solute and solvent, and on the temperature of the solution. For example, more sugar will dissolve in hot tea than in cold tea. Dissolved particles move randomly through the solution. Some particles will collide with undissolved crystals and may reattach to them. When the amount of solute reattaching to the crystals equals the amount dissolving away, solution equilibrium is reached. If we raise the temperature, we see that more solute goes into solution, until again solution equilibrium is reached.
Okay, so solution equilibrium is another kind of key term that we have for this section, okay? And that just means, you know, you have these ions in solution and they're going to be forming, kind of reforming the crystal lattice at the same rate that other ones will be leaving, okay? And that's called solution equilibrium. Now, here, so for example, here I have a solution of salt water, okay? Now, take a second and see if you can figure out, is this, oh, haven't quite done that yet. So here at the bottom, okay, I have leftover solid sodium chloride, which means that this process is all happening, okay? Now, I can, if I were to take just water, all right, and start adding salt or sugar or something to it. In this case, we're adding sodium acetate, okay? And we're dissolving sodium acetate in water, okay? As you start to add sodium acetate, the mass in grams of sodium acetate added to 100 grams of water at 20 degrees Celsius, okay? Mass in grams of sodium carbonate dissolved in 100 grams of water. So if I put in, what's this, 5 grams, okay? If I put in 5 grams of sodium acetate into this water, I'm going to get 5 grams of sodium acetate dissolved. Okay, down here, we say that this is unsaturated. Okay, if a solution is unsaturated, more solute can be dissolved. No undissolved solute remains. Okay, so down here, I could add more and I'd still get more. Now I'd keep doing this and I'd keep doing this. Then I'd get to a point where it would start to look like this, okay? Where I'd keep adding solid, and what I would get is just more solid at the bottom. I could never get more to dissolve, okay? Now, this point we call, this kind of solution we say is saturated. If the amount of solute added exceeds the solubility, some solute remains undissolved, which means that the solution just has as much dissolved solid, as much dissolved solute as possible, okay? And this point, this value where this happens, is called the solubility of a substance. All right? Now, solubilities are temperature dependent. Okay? You saw that from the video. If you increase the temperature, you're going to increase the solubility. Well, what happens if you increase the solubility? If you increase the temperature, okay, you increase solubility, you make a bunch more, you can add some more solute to your solution. And then what happens if you cool it off? Well, initially, you're just going to have a solution, okay? And that solution we're going to call supersaturated. Okay? Let's say that we've put in our 46.4 grams of sodium acetate into this 100 grams of water. And then I raise the temperature and I'm able to add, let's say, 3 more grams. Okay? When I lower the temperature back down to 20 degrees, okay, I still have 49.4 grams of sodium acetate dissolved in solution, so we call that supersaturated. Okay? Now supersaturated solutions will always return to saturated solutions eventually. And if you've ever made rock candy, this is a great example, okay? What you do is you take sugar water and you boil it, okay? And you get as much sugar water in as you can. Then you boil the water, okay? Get it hot, all right? And then you take that off and you like pour it into something. Okay, maybe you keep it in the pot. I don't know. Maybe your parents need to use the pot for cooking and they're annoyed that you're making rock candy in their pot that they need to use for cooking. I don't know. Okay, maybe you put it into like a cup or something. Then you put a string in and crystals will start to form on that string. Okay, and you'll eventually get this big mass of sugar crystal that's on this string in the solution, because it was a supersaturated solution which went back to a saturated solution. Okay? So, how can you tell if something's going to be soluble? Okay? The easy answer here is that, and the one that I want you to remember, is that like dissolves like. Well, what does that mean? Okay? That just means that similar compounds will dissolve each other. Well, how do you decide if a compound's similar? Okay? You would look at kind of 3 things. The type of bonding within a molecule. Okay? So covalent compounds will tend to be soluble in covalent compounds, and ionic compounds will tend to be soluble in with ionic compounds. Okay? 2, polarity of molecules or not polarity of molecules. And 3, intermolecular forces between the solute and the solvent. Okay? So, what are some examples of this? Well, I'm going to use some terms here. Okay? I'm going to use these terms miscible and immiscible. And these terms are used to describe liquids. Okay? If you have 2 liquids, miscible means that they're able to dissolve in each other. Okay? Immiscible means that they cannot dissolve. So I'd like you to think about like mixtures of 2 liquids that you think would be miscible and things that you would think would not be miscible. Okay, pause it, think about it. I'm going to come back and we'll go over it. All right. So oil and water. So if you've ever taken olive oil and put it in water, okay, what you'll get is you'll get a layer of oil on top and the water below, because water has a greater density than oil, so water floats on the bottom, oil floats on top, but they don't mix. Okay, this would be an example of an immiscible solution. Okay, now why is that? Well, here is oleic acid. Okay, and oleic acid is found in a lot of oils. Now, if you look at this thing, there are a lot of carbon-hydrogen bonds, which means that this whole half of the molecule, holy moly Batman, is not polar. Okay, and you try to put that into something like water, which is highly polar, and it's not going to work. Okay, what ends up happening, you'll notice that this end is actually a little bit polar. Okay, so what'll happen is you'll get a bunch of these that form micelles, or lipid bilayers. Okay, where you have a fatty end that all points into the middle. Okay, where like the nonpolar tails can be around like, and these nonpolar, these are called carboxyl groups, nonpolar groups, all sit on the outside where they can interact with the water. Okay? But anyway, oil and water, not miscible, okay, or immiscible. Now you compare that with water and rubbing alcohol, okay, or water and ethanol, okay. Those do mix because they're similar enough, okay, that the water, which is polar, can interact with the alcohol, which is also polar. Okay. Another one is oil and dry cleaning fluid. I don't know how many of you actually use dry cleaning fluid all that often. I don't. So this one's not that great for me, but it goes to show you have your oil, which we already know what that looks like, and then we have tetrachloroethylene. Okay, that's C2Cl4. So what does that look like? C2Cl4. Okay, now as you can see, this molecule is symmetrical, which means that there's no dipole. Okay, it's very similar to something like this. Okay, which is tetrahedral. Okay, about this central carbon, and so it's a completely symmetrical molecule, so no net dipole. Here, this is trigonal planar. Okay, and there's no net dipole on this molecule either. Okay. All right, so that's sort of like dissolve like in nitty-gritty detail. All right. So here's just a table. This is from your textbook. The solubility of solutes is a function of temperature in grams solute per 100 grams of water. So it's really easy to see the trends. Just kidding, because it's in a table. Why don't we put it in a graph? So here we go. Here's our graph. As you can see, these are all ionic compounds, you'll notice. So most of them, their solubility increases as temperature increases. All right, now that makes sense, right? The water has more energy, it's better able to break up the crystal lattice structure, so you should see an increase in solubility. Some of them don't, but don't worry too much about that. Now, this is interesting. This is for gases. All right? As you increase the temperature, the solubility of a gas actually decreases because, right, the gas molecules have more energy, and if they have more energy, then they have more energy to break the intermolecular forces that are holding them in solution. And I'm pretty sure I have a video of all this stuff. Here's
Solutions that
a
are
video of
miscible mix or
miscibility.
dissolve in one another. Those that are immiscible do not mix. Toluene and water are immiscible. Toluene is highly nonpolar, while water is highly polar. When mixed, the two unlike liquids form a definite boundary where the toluene ends and the water begins. This boundary is called an interface. Ethanol and water, on the other hand, are miscible. In any proportions, the ethanol completely dissolves in water. There is no boundary between the liquids.
Okay, and then here's our
The
gas.
solubility of gases in liquids is an equilibrium process. When gas is present at the surface of a liquid, there is a flow of gas molecules into and out of the liquid. If we increase the pressure of the gas...
Okay, so now this is, it's going to start talking about pressure. So I just want to go back and think about, so temperature we saw, so as temperature increases, the solubility decreases for a gas. Okay, for a solid, okay, as temperature increases, the solubility increases. And I may have you use that for something on the test, okay? So be aware that that's coming. So what about the pressure? Okay, well, the pressure is we're gonna have a very similar situation to the temperature, right? So let's watch the video.
The solubility of gases in liquids is an equilibrium process. When gas is present at the surface of a liquid, there is a flow of gas molecules into and out of the liquid. If we increase the pressure of the gas over the liquid, the equilibrium is shifted towards reducing this pressure by increasing the amount of gas dissolved in the liquid. If we decrease the pressure of the gas, such as when we open a new container of soda, the equilibrium is shifted towards reducing the amount of gas dissolved in the liquid. Consequently, the carbon dioxide rapidly fizzes out. On the other hand, if we increase the temperature, the molecules in the liquid have more energy and move faster, making it easier for the gas molecules to escape the solution. If we decrease the temperature, molecules have less energy and move more slowly. If gas molecules are moving slowly enough, they will not be able to overcome the attractive forces of the solution.
Okay, so that kind of sums all that up nicely. So I think soda is a great example of this, or pop, or whatever we're calling it these days. Let's say we're bottling Coke, okay, at the factory. So you'll take your uncarbonated Coke, your just flat mixture of sugar and flavoring and water, okay, there's no carbonation at all, and then you'll bottle it. So we'll bottle it under, let's say, 4 atmospheres of carbon dioxide. Okay, now when you do that, that's going to force some of the carbon dioxide into solution, okay, because that's a high pressure. All right, then when you get your bottle of Coke and you open it, okay, you go down to 1 atmosphere, okay, and even more, you'll let in other gases. So the partial pressure of carbon dioxide will decrease even more. Okay. Now, this means that the carbon dioxide that was dissolved in the soda will escape. And that's what that bubbling is. Okay. So this is just an example of how pressure affects the solubility of gas. And that's all we got for today.